enter, and point. It will go in the cloud. So from now on, yes, the recording sign is on, and we can restart sharing. All right, here we are. So all the information, let me first tell you that the main communication channel with you is through my website, okay? And those of you who were students of the Space Environment course know how to use it. All the information, the exchange of information occurs through the website for now. We may switch, I may switch to Classroom, and we will see. All the recording sessions recorded sessions, lectures will be put on Google Drive, and I will give you the address. You can also find my classes of last year on YouTube, because last year I was using YouTube rather than Zoom, because essentially you told me that you preferred YouTube for some reason. So you can also have access to my lectures of last year, of the past year on YouTube. You do a search and you will find them. This year we will use Zoom because most of my colleagues use Zoom, and I think I was the only one to use YouTube last year. But anyway, you will have access to the recording in any case. And this year, I will change a little bit the course. What are the goals of this course? They are essentially stated here in this question. We will try to answer to some questions. And the questions are, how do we know where a spacecraft is and will be at a future time? So this is the problem of navigation, the fundamental problem of spacecraft navigation. Okay? And it's a crucial problem to navigate a spacecraft. We will not tackle the issue of orbital maneuvers. So the maneuvers needed to place a spacecraft in a desired orbit, because that has been done already in a previous course, in the spaceflight mechanics course. All right? We will tackle the problem of orbit determination, how to determine the orbit of a spacecraft. So to know where a spacecraft is, what is its velocity, and where the spacecraft will be at a future time, and what will be the velocity at a future time. So this is the fundamental problem of space navigation. Then another important question is, how do we know the spatial orientation of the spacecraft? So how is oriented a spacecraft with respect to a given reference frame? And we will see that there is a number of reference frames that we can use. How is the spacecraft oriented in space? And of course, this is another essential problem, because how can you run a mission without being able to point an instrument, say a camera, in a given direction or to a given point on a planet? This is the problem of knowledge. knowledge of the orientation. The other problem related to it is how do we control the spacecraft orientation? Attitude, determination, and control is made up of two pillars. One pillar is knowing how the spacecraft is oriented. The second pillar is how do we control the orientation? How do we actuate torques that rotate the spacecraft in the desired position? So we will answer this question as well, at least in some simple cases and for certain spacecraft, for three-axis stabilized or gravity gradient. We will say something perhaps on spinners, because the control of a spacecraft and also the determination of the attitude is different depending on the type of spacecraft. Three-axis stabilized, spinner, or dual mode. There are spacecraft which have a part which is spinning and a part which is inertially fixed, for example. Then, what is the infrastructure for spacecraft navigation? So all the ground segments. How is the ground segment done? How do we gain access to the fundamental quantities that allow us to navigate a spacecraft? Range, range rate, angular measurements, etc. So how are the tracking observables generated? And this is something which is in between, let us say, traditional aerospace engineering and telecommunication engineering. And then, most important, what reference frames and timescales are we using? Because knowing where a spacecraft is and at what time the spacecraft is in that location requires a definition of a time scale and the definition of a reference frame. And today, for very precise applications, this is crucial. We need to know exactly how a reference frame is defined and what a reference frame is. Then, and we will start with this topic this year, what are the main categories of space missions and what are their system level characteristics? So, and the related question is, how are space missions conceived and how are they developed and operated? So this is part of classical system engineering. And I would like to tell you one thing. After this course, you will certainly not be able to proclaim yourself to be a system engineer. System engineering is relatively simple and also terribly boring in a sense, if done in a certain, for example, you can take some reference textbook that we will see also. You can download them from the web, and their reading is terribly boring when it's not applied to the definition and the realization of the physical mission. Okay, system engineering is something, and a good system engineer is an engineer who has seen many different cases, has a lot of experience, has probably made many mistakes, and essentially experience is everything. When I go to meetings and now I go to virtual meetings, but when I participated in meetings and everyone has to present himself or herself, and I see some young engineer at Estec, for example, I see the system engineer, etc. Okay, I think, okay, fine, you are at the start of your career in system engineering, because a good system engineer is someone who really must have a lot of experience. Experience is everything. Pretty much in surgery, or to be a good neurosurgeon, you need a lot of experience, okay? And probably also need to commit some mistakes and learn from the mistakes that you made. So these are fundamentally the questions we will try to answer. And for textbook and material, everything is written also on, you can find this on the on my website and also on the page, on the GOM page of university, of my university. So for orbit determination, a suggested textbook is this one, Tapley, Schutz, and Born, Statistical Orbit Determination. Is a beautiful book of outstanding clarity. It's a benchmark for how a book should be written. And it took them, the authors, I know two of them, it took 10 years, even more, to write that book. For attitude dynamics and control, we will use, or you can use CD, Spatial Dynamics and Control. It's also a well-done book, not at the level of the first one, but it's not too complicated as a sound engineering approach to the problem. But I have the, let us say, not the pride, I think that the view graphs of the course will be enough for you to pass successfully the exam, and so the material that I will distribute throughout the course is enough. All right, is enough. How do you find this material? Let me see if I have not written it, but what we can do, I will write it here. So if you go on my website, the website radioscience.dima.uniroma1.it, and you go in the section for students, you will find on the left a menu, and there you can find course material. You go in, and to access to the course material, you have to use this user ID. Underscore. And the password MSS underscore ESS underscore 2010. All right. So why do I put a password? Simply because in the slide I use material that I cannibalize from the web. They are images that I copy from the web that help me in providing, in simplifying my job. And they are much better quality than the one that I can draw on the board or that I can do myself. And I don't check the copyright material, whether this is copyrighted material. I don't check. I always cite the sources, but it cannot be public. And this is the reason why I put this material under password control. All right. So if you go to the website now, you will find some of you may check whether it works or not, because I go by heart. Let me say that yeah, it's essentially for protection, for my personal protection. All right. Most of the material are public images, NASA, etc. Sometimes I don't give the full credit I should, but this is the reason why it's password protected. You will find the material of last year. I'm doing some updates. Every year I update a little bit. So I will upload each module when it's completed and when it has changed significantly. And you have just to download it. You have the PDF, download it. And I really suggest you not to print anything. Save paper, okay? You are young, I think you can, without any problem, study on a computer, on a tablet, etc. So don't print it, also because it's going to change. And the page numbers are changing. So far for the material that I will use during the course. And what about the exam? Also, this is described, the way in which I do the exam is described fairly clearly on my website. But let us say it in words now. So, first of all, during the course, I will give 2 or 3 homework. And this homework generally entail the solution with a code, MATLAB, you can use Python, you can use whatever code you wish, of, say, an orbit determination problem, an attitude determination or control problem. And generally, I give the homework, I publish the homework on my website on, say, Tuesday or Wednesday afternoon, after classes are over. And you have essentially time till Sunday at midnight to email me the solution, which is made up by a very simple and synthetic note describing the procedures that you have followed to solve the problem, and a working code, a code that works. So we can take the code, a MATLAB code, for example, run it, press a button, run it, and obtain the results. Okay? And these homeworks are not compulsory. So you may decide not to take them. And the outcome is just pass or fail. Pass or fail. There is no, I don't give marks for this homework. So if you pass both homeworks, you have access to the final exam in simplified mode, let us say. Simplified mode means that the exam is faster, generally faster, shorter, and you don't have to go through a multiple choice test. If you pass successfully the homeworks, you have access to the exam in simplified mode. All this is clearly written on my website and also on the university site. Okay, understood? So if suppose that you don't want to take the homeworks, or you fail one or both homeworks, then you have to take, before the exam, in order to be admitted to the oral exam, you have to take a multiple choice test. The multiple choice test is made up by 15 questions to be answered. There is no need to take note of what I'm saying, because everything is written on the website. 15 questions to be answered 20 minutes. All right. After the, let us say, within an hour, even less, we give you, on the basis of the multiple choice test, the maximum score grade that you can get at the oral exam. Okay? So the multiple choice test has the function, the goal of providing you an idea of the level of your preparation to the exam. Okay, so on the basis of the number of answers, and there is an algorithm that you can go and read on the website, that determines the maximum grade that you can get. Say 23, and I tell you, okay, what's your name, for example? Yes. Lau? Baldanza? Baldanza, 28. And probably you will say, yes, I accept. Also because if the oral exam is done done very well, so if you do very well at the oral exam, you can increase up to 3 points the outcome of the multiple choice test. Because there are cases of people who are really, and it happened to me sometimes, who are really well prepared, and I can see that when I for example, they take a low score, 23, for example, at the multiple choice test, and then at the oral exam, they do extremely well. You can increase up to 3 points. So from 23, go to 26. But you can go also below the outcome of the multiple choice test. So you can also even not pass the exam. Okay? So that is just an indication. If you pass both homeworks, you have not to take the multiple choice test. All right? Everything clear? Are there questions? Also from remote?
Posso fare una domanda?
Sure.
Posso farla in italiano o devo farla...
You will do it in Italian, I will repeat it in English.
Se uno passa entrambi i test, per quanto sono validi, diciamo, ai fini dell'esame?
Till now, forever. Okay, so I'm quite generous. So I'd say I continue. Let us assume that also if you take the exam, then the following year, I consider them as valid. Okay?
Ok.
E invece posso?
Yes, please.
E invece, sempre se uno ottiene il pass ad entrambi questi test su MATLAB, e poi ha un voto di partenza per l'orale o il voto è basato soltanto su come si va all'orale?
No, the two are completely independent. So the question is how the outcome of the MCT test influences the final grade after the oral exam, right?
Sì,
I
sì,
think
sì.
this was the question. There is no correlation. The outcome of the MCT test tells you only the maximum grade that you can get at the oral exam. So suppose it's 26, the outcome of the MCT test. You know that if you are doing an outstanding oral exam, you can go up to 29. But if you do poorly at the oral exam, you may have to retake the exam, or you can get a much lower grade, for example, 20. Clear? So it determines only the maximum grade that you can get.
Perfetto, grazie.
Minore o uguale, plus the 3 extra points bonus, because I realized that there were students who don't like multiple choice tests. For some reason, I don't know whether you are some of those member of that population, of that group. And they are doing, however, quite well, extremely well at the oral exam. Sometimes I try to convince them to take the exam again, because there are cases like this. All right? One thing about the homeworks, I really and strongly suggest you to take the homework. They are problems that require some effort to be solved, but you will have the opportunity to work yourself a code and apply the concepts for orbit determination, of attitude determination, or attitude control. So it's very, you will learn a lot by solving that problem, especially if you do by yourself, right? Without the help of your fellow students or classmates. So I really encourage you to take them and to solve the problems by yourself. You can certainly exchange, and I'm pretty sure it happens, you can exchange ideas with your fellows, etc. But the writing of the code and the final note must be your work. Okay, don't cheat. In 2 words, don't cheat. All right, because you will lose the relevance, the importance of these homeworks. And I give you essentially 5 days to solve it. There is one thing, however, an additional, not test, but there is a competition, a challenge. The challenge allows the winners to gain points for the final exam. It's a problem generally more difficult than the other ones, and it has to be done in a weekend. So in this period, there is not much to do during weekends. You cannot go to the beach or doing other things. And in a weekend, you have to, again, send a working code and a note, a technical note. And the winner gains 3 points at the final exam. There are 2 second prizes, 2 points each, and 3 third prizes, 1 point each. And again, I suggest you to do it. It's there is a lot to learn by solving that problem by yourself. All right, and in that case, being a competition, I think there is no cheating, right? By the way, if you do the challenge and you failed one of the 2 tests, one of the 2 homeworks, the challenge is a good replacement for the test that you failed. All right, so it's a sort of jolly that you can use. So, having said that, questions, please.
Un solido rimpiazzo significa che bisogna vincere un solido rimpiazzo o bisogna farlo?
You must do it. So the question is, must I win the challenge to be able to replace a failed homework? No, you need not to win, but you need to do it decently, at least answer some questions, because generally there is a number of questions to be answered in the test, in the challenge, and if you answer correctly we will see 2 or 3 of the questions, that's enough. So you need not to win, okay? But there is a lot to learn with with these tests. All right. Did anybody try to log in to the site of the slides to see whether it works or not?
Sì, funziona.
It works perfect. No, because I was afraid that the password might have been wrong, so I remember it. So, other questions? What time is it? No, we have still 25 minutes. So we don't do the break this time. Do you agree? Okay, excellent. So, questions? Excellent, no questions. So we can go to the first part of this course, which deals with, let us say, system engineering. So we will go through a quick overview of the different type of missions and give a general description of their main characteristics, and then we will speak a little bit more in detail about mission phases and the tasks of system engineering. So let us start with this broad classification of types of missions. And let me see if I can use the laser pointer. Yes. Okay. Do you see the laser pointer? Yes. So let us start with the Earth observation satellites. For example, in the ESA, European Space Agency budget, Earth observation is the largest chunk of the budget. And there is a number of glorious missions like Meteosat, Landsat, GRACE, GOCE, CSAT, etc. Now Cosmos SkyMed, the Sentinel group, and so on, all devoted to Earth observation. And they are used both for scientific investigations and to provide information useful, for example, for weather forecasts. Why such a big effort? Well, because, of course, we know that many things are changing on our planet, and we need to monitor these changes. What a better place to monitor globally changes occurring on our planet than space. And this tells you also the type of orbits. You can imagine the type of orbits that Earth observation satellites are putting. They are around the Earth, of course. From geostationary orbits, and these are especially satellites used for weather forecasts. There are many, looking at different parts of the Earth, doing continuous measurements, and we will see also what kind of measurements can be done. From this vantage point, which is the geostationary orbit. But there are also many Earth observation missions that require LEO orbits, low Earth orbits. And these are, for example, suppose that you want to map the gravity field of the planet, of the Earth. We know what the gravity field is, but if you want to map the variations in the gravity field, which is associated to the transport of liquids, of course, you have to stay low, because the lower you are to the places where these changes occur, the better you can detect it. And there was a fantastic mission called GRACE, which is based on satellite-to-satellite tracking. We will perhaps see something on GRACE. I have to add some slides, which told us how, what is the periodic variation, for example, of the water table locally on land. Water table is in Italian faglia freatica, so the water contained in the water table and their seasonal changes. Is the water table depleting or not? It tells also many other things, like the melting of ice. The melting of ice in Greenland, in Antarctica, etc. So this is another Earth observation satellite. Classical Earth observation satellites were devoted, for example, to measure other parameters like humidity, like winds, like, for example, yes, moisture, the amount of vegetation, and you can do a lot of things from space, even estimate the amount, how productive a crop will be in a season, in a given season. All these satellites are generally low Earth orbit and polar, because you have to cover essentially the entire planet. I say polar, may also be at high inclination, of course, not necessarily 90 degrees, because the polar region for certain applications may not be so attractive, but we can say LEO and polar. You can gather a lot of information for spectrometer, visual or infrared spectrometers. The spectrometers are instruments, it's not written here. The spectrometers are instruments which provide the spectrum of each pixel of an image. So they are called imaging spectrometers. So imagine to have, let me go here, to have, I have to take the pen. How do I get rid of the laser pointer? I do it here. Pen color red, first of all. Second, I do from here pen. All right. So imagine you have a camera which provides a CCD. which provides for each pixel an intensity, okay? An intensity, and our cameras provide for each pixel of the CCD an intensity, and you build up an image by looking at the intensity in each pixel. Now, imagine that in each pixel, on the contrary, rather than providing an integrated number, which is the intensity of light in that pixel, you do something else. You have a full spectrum of the radiation coming from that particular location on the Earth, which corresponds to a given pixel, for example, this pixel here. So rather than having one number, 256 bits, for example, you get a full spectrum. So essentially, you build the so-called image cube, because there is another dimension here for each pixel, which is the frequency of the wavelength, lambda, of the radiation that is coming. Okay, so for each pixel, we have this additional information. And imaging spectrometers are one of the most useful instruments for monitoring land. Okay? There are more specialized, and also in planetary spacecraft, they are on board every planetary spacecraft. So there are also more specialized instruments, water vapor radiometers, which measure the water vapor content in a column. There are spacecraft which are able to measure the electron density in the ionosphere, and so on and so forth. So many of them, a variety of payload, and each of this payload has its own requirement. You want to ask a question? So has its own requirements. For example, imaging spectrometers generally require cooled detectors. So require a cooling system. And this implies that, for example, there is a side on the spacecraft which cannot be exposed to the sun. And this simple constraint has important implication on the spacecraft design. So Earth observation satellites are a large class of satellites carrying different payloads, generally in LEO orbit, LEO-polar orbit, or geostationary orbit. Other important spacecraft of this class, Earth observation, are those spacecraft carrying altimeters. And altimeters can be radar altimeters or laser altimeters. And we will see an example of an altimetric mission. Altimetric missions are important because they can provide information on sea level changes. and also on especially laser altimeters, on the depletion of ice that we find in certain regions of the Earth. And we will talk a little bit about this. I will describe the mission JSON 1, JSON 2, and CSAT. The first mission of this type, really fantastic, was called the CSAT, and provides information about especially sea level changes. You know that global warming is causing an increase in the level of the oceans. But one important why? Because ice is melting in Antarctica, in Greenland, in part in South America, etc. In South America, actually less than elsewhere. Where does all this water go? You may imagine that all this water that melts goes into the ocean. But this is not necessarily true, because part of it may go in the atmosphere and part of it may return on land and replenish the water table. So you know how much water you are melting, much ice you are melting, how much liquid water you are producing, but you don't know what is the sea level increase. And there are indications, the measurements need to be more precise, that half of the ice that melts goes into the ocean and half goes elsewhere. So there is a mismatch between the melting of the ice and the sea level change, which is, in a sense, maybe a good thing. Remember, however, that water vapor is a greenhouse gas, okay? And greenhouse has the effect of raising the temperature, the average temperature of the planet. So in this quick list of mission types, there is a space also for, they are not put in any special logical order. Technology demonstration missions. Sometimes you need to demonstrate certain technologies in space before using them on an expensive mission, for example. So you want a demonstration. You want to demonstrate that it works. And this class of mission is a mission which bring on board a payload of a given type, or they can be used to test the endurance of certain materials to the space environment. So, for example, you have a platform with material, a number of materials, etc. You put them on this platform. The platform stays there for 5 years. Then you go there, retrieve the platform, bring it to Earth, and with the tools available in ground labs, very sophisticated, you see the damage and how the different materials reacted to the exposure to radiation, to UV, etc., etc. These are the so-called, is a type of technology demonstration missions. ESA, for example, has done a technology demonstration mission, Smart One, I had an experiment on board that tested a Ka-band transponder, XKA transponder, but they wanted to test an electric propulsion system based on stationary plasma thrusters. And this mission went to the moon. And also did some of the observations. But before using that particular engine on a much more expensive mission, you try with a small spacecraft of limited cost the technology that you want to test. I'm not really a fan of this technology demonstration mission because today also our capability to test on grounds, to do ground tests are quite good. But in certain cases, they were useful. For example, I have an example, the mission LISA Pathfinder, you may have heard of it from the press. The LISA Pathfinder is a pathfinder to a much bigger mission called LISA. And LISA is a set of 3 spacecraft placed at 5 million kilometers from each other in Earth orbit, on the same orbit of the Earth, but they trail the Earth. Okay, so they are not in Earth orbit. They are in heliocentric orbit, trailing the Earth. Okay, they are not rotating about the Earth. And they shoot lasers to each other. And with these lasers, you can produce interference fringes, and with these interference fringes, you can detect low-frequency gravitational waves. So it's a mission for the detection of gravitational waves. It's called LISA. It will be launched in 2034. Now, it's from the engineering point of view, is extremely challenging. Because you need to have masses which are subject only to gravity. To feel a gravitational wave, okay, you want a mass that feels only gravity. You don't want the mass to be subject to stray accelerations such as infrared radiation pressure. So you have a proof mass inside the spacecraft, okay? Each of the 3 spacecraft, you have a proof mass, and you want to see the distance, how the distance between these 2 proof mass placed at 5 million kilometers away from each other changes with time. If a gravitational wave which perturbs the fabric of space-time creates a variation, okay, in the distance, the laser system detects it. But it's essential, absolutely essential, to avoid any non-gravitational acceleration of these proof masses. If you have, for example, the cage in which this proof mass is placed with a differential temperature, one side slightly colder than the other, infrared radiation pressure is unbalanced and the mass moves. And this interferes, of course, with the detection of gravitational waves. So it's extremely challenging from the point of view of engineering, of mission design. And for this reason, ESA wanted a demonstration called the LISA Pathfinder, which in a small spacecraft has 2 proof masses, one side slightly colder than the other,
Infrared radiation pressure is
Excuse me,
available.
hey, could you please close your microphone? Because there is an echo. So, wanted to test the concept by using two masses separated by 1 meter inside the spacecraft with a laser system. And these two masses were essentially drag-free. So free from non-gravitational acceleration. And it was a very successful mission because it went beyond specification on acceleration noise. So this is another type of technology demonstration mission in the science, for a science mission. Okay? They are testing today on Mars. You know that the rover Perseverance has arrived on Mars, but it had a companion whose name is Ingenuity, which is an helicopter, 2 rotors helicopter. And they want to test this little drone, which is not different from the one that we can purchase for a limited amount of money, few hundred euros here. They want to test it on Mars. We will see how it's made. The blades, the rotor blades are about 1.5 meters. And they want to test these concepts. Also, this can be conceived as a technology demonstration mission. All right, so we will go through all these missions tomorrow, and we will see also some examples. All right. So very good. I think we can quit here. And sorry for the technical problems. I will that I didn't expect. And if there are questions, you can email me if you want explanations from home, or you can ask now. So if there are no questions, I stop sharing and stop recording.